Okay, off we go. So last time we were, I say we, y'all were looking at videos from last time I taught this class or something, looking at injectivity and surjectivity and stuff like that. And what was the purpose of that? Well, side note, there's various different situations where it's important to understand these ideas. But what we were building up to in this moment was the idea of invertibility and what it means for a function to be invertible. Which is important because sometimes you need to invert a function, and the function had better be invertible if you want to invert it. Right? So here's a couple of examples, some commonly mistreated matters, and let's talk about the square root. And a lot of people will tell you that square root is what you get when you undo the square. Right, and so that's what they told me in elementary school was that you square a number, right? Well, square root just means you kind of just undo that process. And it's just not true. It's just not. I mean, here's the squaring function. You can square any real number, for example, right? And this function, as written here, is not invertible because there are lots of real numbers that have multiple square roots, right? Typically a plus and a minus, right? There are also lots of real numbers that have no square roots, right? So if you were to try to invert this function, what you're going to get is not a function in general, right? Okay. All right. So this function, though, is invertible. And you can make this invertible by restricting the domain, restricting the target, in some sense to kind of avoid all the problems that we just made fun of f on the basis of. So this function, you take any non-negative real number and talk about its square roots. It might have two of them, but only one of them will be in the domain of this function. All right, so that's an invertible function, and the square root is the inverse of that g written right above. Okay. All right, now here's another example, and I've seen this treated very poorly in the past when I was in high school. I didn't realize it when I was in high school, but in retrospect, yeah, it's super tragic the way that this got presented to me in high school. Sine, by itself, if you just say sine, you can define sine for any real number, right? You just go around the unit circle that, by that angle, whatever, and whatever's the y-coordinate, that's sine of that angle. It's fine. That function is not invertible. So you have to restrict your domain correspondingly, and the typical standard choice for this is to restrict your angles to these values, which I like to visualize on the unit circle, would be these angles right here. And then rather than sort of pointlessly, sloppily saying, let's let the target be all of R. Nope, let's make it tight, just exactly these values that actually come out. Namely the actual y-coordinates that are y-coordinates of points on the unit circle. Right? And if you restrict your attention like that, then this is what I call the invertible sine function. This function, here's its graph. That function is invertible. You give me any theta, there is exactly one y, but also for every y, there is exactly one theta. Arguably better understood by, instead of looking at the graph, just look at the unit circle. You give me a theta, there is a corresponding y. And vice versa, you give me a y, there is a corresponding theta by just moving horizontally across. Right? So sine and arcsine, both represented here in this same picture. Everybody happy? Okay. All right. So a little bit of language that has to get noted. We're going to talk about various different kinds of functions that have various different numbers of inputs, various different numbers of outputs, and the number of outputs refers to what we call the values of the function. And if there is only one output coordinate, then the output is just a real number, so we call it a real valued function, or said differently, that value is a scalar, and so we call it a scalar valued function. Okay. On the other hand, what comes out, you might have several outputs. Said differently, you might have an output that has several coordinates, but another way to say that is that that output is a vector, and so in that case, when m is greater than 1, we talk about a vector valued function. So heads up for that terminology. If you hear real valued, that instantly tells you there's a single output coordinate. If you hear vector valued, that means that there are multiple output coordinates. Okay, and then likewise with the inputs. The term variable gets used here. This is just kind of a terminological convention. When we say variable, we're talking about the input variables as far as this terminology goes anyway. And so single variable means one input variable. Multivariable means several input variables, specifically input variables. Okay, again, just terminology. Okay, a real quick observation about component functions. So now let's talk about this original function f we were looking at, several in, several out. So all of these output variables depend on the x, several x input variables. But in addition to all depending, they also individually, one at a time, depend on all of those input variables. So if you look only at y1 by itself, y1 is a single real value. But the value of that y1 will depend on all of these several input variables. So this, what we call component function, the first component function, is a function from Rn, because we need all of the inputs. But since we're only looking at the one output, this is real valued, whereas the whole function might be vector valued. Yes?
Could you please repeat what you said about y1 depending on all the input?
Yeah. So when we say that variables are functions of input variables, well, depend just means on that the values are determined on the basis of the values of the input variables.
So all of them.
Yeah. Well, I mean, when we say, if I say f of x comma y equals x, that's a function of x and y, even though the y doesn't show up in the formula, right? So it doesn't have to actually manifest, right? But the point is it's allowed to. Yeah, right. Okay. And just an example. This is not an important example, but I like to point out that when we're talking about vector valued multivariable functions, this sounds like we're talking about some extremely specific, narrow, possibly niche kind of a thing. And it's really important that we recognize that it's not. Vector valued multivariable functions are the norm. Most functions in the real world that if you're dealing with some actual scenario out there, most of the time you're talking about a vector valued multivariable function. Just to drive this home, let's talk about the weather, right? This is not niche, abstract, weirdo kind of a scenario. This is the most trivial of trite water cooler conversations, right? And yet it's multivariable because there are several input variables that determine the weather. Right? Weather depends on all of these things: latitude, longitude, altitude, how high up above the ground are you, time, right? Are you talking about now, or are you talking about last week? Or are you talking about in 10 days, right? So the weather depends on all of these inputs. And what do we mean when we're talking about the weather? We're talking about various different aspects of weather, all of which depend on when, where, and how high are you interested. Everybody on board with that? Okay. All right. So, these are not niche considerations. This is how do we understand most functions? Okay. So now we're going to talk about how to visualize functions, and this is an underestimated topic. A lot of people will look at the what we're about to talk about, and we're going to draw some pictures and stuff like that. And a lot of students mistakenly look at the amount of algebra that's involved and what kinds of algebraic manipulations, and are we going to be dealing with big polynomials, or are we going to be factoring, or are we going to be using the quadratic equation, are we going to be doing any calculus? None of that's going to come up in what we're going to talk about here. And so a lot of students think, oh, that stuff's easy. And that's a mistake. The challenge with visualizing these kinds of functions is not in the brutal algebra, because there isn't brutal algebra typically. The challenge is in making important distinctions between different kinds of constructions that lead to different kinds of pictures, understanding those distinctions, using the terminology correctly so that your listener can make the distinctions that you've made, right? And just being generally careful about all of that stuff. It's surprisingly difficult. One of the things that makes this hard for a lot of students is that a lot of students went to high schools like mine where they let you get away with all sorts of, semantical crimes. And they let you say one thing that doesn't actually make any sense, but they knew what you meant, and so they're like, okay, I knew what you meant, and that's fine. But what that leads to is ultimately confusion later. And so this is what you're going to have to work against, and I urge y'all to be really sort of careful about this. Don't underestimate the importance of saying things correctly and saying things precisely, because if you are confusing your listeners, well, that's one thing, right? But you are also listening to yourself, and you will confuse yourself, and you will not just use the terms incorrectly, you will get wrong answers, and your bridge will fall down if you're not careful about this kind of stuff. Right. So anyway, like I say, please do not underestimate the level of challenge in the next several pages of what we're going to be talking about here. Okay, so first let's talk about graphs. I know y'all have seen graphs before. Here's the standard example that everybody probably remembers from Calc 1 type classes and prior. And you might not have used this notation, but again, this is pretty standard notation. This notation means my function's called f, the domain is here, it's R1 in this case, and the target is here, are also R1 in this case. Okay, so the idea of a graph is that we're going to take input values, which might in general be an entire vector of coordinates that go into the function. We're going to list all those input coordinates first. And now in this case, here, let's see, what goes in is just the coordinate x. So we're going to list that first. And then we're going to take the corresponding output values. Now again, what comes out of the function? I guess we'll call that y. Let's say, again, possibly several coordinates in the y vector. And we will list those next, just right after your input variables. So likewise here, what comes out, we list next. And then, that's the output value. And then we're going to do this weird thing where we take this list, let's recognize strange list, where we have both inputs and outputs in the same ordered pair in this case. That's weird. X is from the domain. Y is not from the domain. Y is from this totally separate world over here, the target. Right? But we list them together, we consider them as coordinates of the same point, and that point is a point on what we call the graph. And if you repeat this for every input value, and think about all the different inputs, right, then you will get a bunch of different outputs. And look at all of these ordered pairs, like so, and that will give you a curve, and that's our graph. Okay, does that make sense to everybody? Yeah.
Could you please repeat from like when we made y equals the output after including?
Can I repeat what now?
After we got the f of x, after plugging in the input variable of x,
Yeah.
then we got y, then
Yeah.
we got using x after that.
So whatever goes in, you list first. When you put that in, different values come out, those go next. And those are your coordinates for what we call a point on the graph, and in this case, that's a point in R2. Yeah. Okay. So here we have a graph, and again, this is the familiar picture. You all have seen these kinds of pictures a million times, and this is all a big yawn, probably, right? But I do want to point out there is something a little bit weird about this, that this is a single variable function, one-dimensional, in terms of what the domain is. So the domain is one-dimensional. The target is also one-dimensional. Why am I drawing a two-dimensional picture? This is a one-dimensional function, which you probably learned about in a single variable calculus class. A little bit of an eyebrow raiser that we're drawing a two-dimensional picture. Right? A little strange. And I'm just saying, right? So the one of the big points here is to recognize that this is not intrinsic to what the function is. We're not drawing pictures like this because we have to, because that's what you do with functions. No. We're drawing this picture because it's convenient for our purposes and we choose to draw this picture. This is a manufactured, made-up construction that we like because of, again, it allows us to draw some pictures that we have a lot of geometric familiarity with. Right? But it is a choice. It is not intrinsic to what functions are. It is just a choice that we make for selfish purposes. All right. Okay, so let's see a higher dimensional version of this. And here we go. We'll think about a function with two input variables. And that means our domain now is two-dimensional. A point in that domain has two coordinates, x and y, that then are the inputs to the function. And, okay, you put that in, and out then comes a single value. I guess we'll call that z. Again, weird though it seems, arbitrary and unnatural though it is, we're going to take that output value and attach it to our input coordinates. Weird, right? Now thus producing, oh no, let me draw that output value on here. It'll be some output value on our sort of target, if you will, like that. And this fairly unnatural, now ordered triple, totally analogous to what we did up here, is a point on our graph. And it'd be about like that. And again, this is just one point on the graph. We're going to repeat this process for every point in the domain. The domain is the entire XY plane down here. It's a two-dimensional plane of points. You'll notice the point on the graph is always directly above the point that is our input. So every point in the plane gets lifted by, different amounts at different points. And so we expect the result then to be a surface. The result of taking a two-dimensional plane and lifting different points by different amounts. So that surface is the graph of that multivariable function. Everybody on board? And again, this is an arbitrary choice. We don't have to do this. We choose to do it because it's nice in certain ways. Yeah?
So do we know which variables are the input by the numbers?
Oh, no, yeah, that's an awkward, sort of ever-present annoyance of, okay, so am I going to explicitly say this, or What does it mean if I do make a choice on that? So yeah, I wrote here z equals f of x comma y, and the suggestion here is I'm saying, look, I would like to think of the first thing that goes in as being called x, and the second thing that goes in as being called y. But there's no law that says that other people using the same function have to use the same choices of variables, but it's nice. It reduces confusion if everybody's sort of on the same page with that. So yeah, typically, you certainly can't infer this from this. Right? The mere fact that I have two inputs, there is no law that says that those inputs have to be, called certain special letters of the alphabet. Yeah.
But the R2, that does anything with the R2 input?
Yes. Well, yeah, that's right. Another way of saying it is that the input is a point in R2. And if you think about what is a point in R2, well, let's say if it's a point, then it has two coordinates. Yeah. Right. Yes.
Can it be like a closed surface, like a sphere?
Oh, no, it can't be because it's a good question. So it does have to be the case that this is a function. And a function means that whatever you put in, what comes out there is a single output. Now that output might have multiple coordinates, but however many coordinates it has, there is a single output. And so in this case, the output is this value z, and that then can only give me a single point on the graph for a given input. Yeah, that's what a function has this rule that for any given inputs there must be exactly one output. Yeah. Yes.
Just to clarify on that, but isn't that just like invertible functions?
One more time.
If one output has only one input value, isn't that just for invertible functions?
Oh, no, I understand what you're saying. It's sort of the opposite. She was asking about one input possibly having multiple output.
But that is
right?
possible.
Invertibility means every output must have exactly one input.
But in the case that a function is not invertible, you can have a closed surface as the result of an output.
If a function is not invertible, then what?
If one input can give you two values for an output, then...
Yeah, that's not a function, though. If one input can give you multiple outputs, then that's not a function.
Okay.
Yeah, that's just a strict rule about what functions are. Yeah. And it's good that we have that rule because that's the only way we can talk about values of a function without ambiguity. Yeah. Is that satisfying? Okay. Yeah. Okay. All right. Now let me show you one more example. Or let me try to show you one next example. And let's recognize, by the way, real quick, that the example we just did, this is the simplest multivariable function that we can even really talk about. I mean, 2 is the smallest number bigger than 1. Right? So this is a barely multivariable function. And again, only one output. Simplest possible case on the outputs. So if I go at all above this simplest possible case, let's look now at a function of 3 input variables. And then, again, one output variable, and we're already in trouble because now I have 4 coordinates. That means that whatever this graph is of a function that looks like that, it'd be a bunch of points that live in 4 dimensions. This is going to be a 4-dimensional picture, and I can't even fake that. Right? Everybody see that? So the first thing I want to say about this is this means graphs, this specific construction, and again, you got to be really, really careful. When I say graph, I mean this specific, precisely defined construction of how to take a function and generate a picture. This specific construction, the graph construction, is very limited in its utility. Basically, other than the simplest possible case, I can't use it. Yes?
Could you graph like the projection onto like a 3-dimensional plane?
Oh yeah, you can make different constructions that you can kind of. There's different things that you can try to do, and it's not so much a projection as a restriction. And you can talk about the restrictions to maybe certain planes inside of R3 or something like that. But to the function itself, the whole function, I'm out of luck. Can't do it. So now when you're doing single variable calculus, let's just kind of recall, flashing back to single variable calculus days, we love these pictures. These are practically all the pictures we ever drew in a single variable calculus class. Graphs are the way to understand single variable functions, right? They're awesome in a lot of powerful ways. And we basically can't use them in all but the most trivial and basic of multivariable contexts. So that's, part of the reason why I think it's really important, don't just hang your hat on the idea of graphs and assume that every picture you see is a graph and decide that every function that you're ever going to deal with, you're always going to draw the graph or you're always going to think in terms of the graph. No, that's a problem. And you're going to run into a brick wall. Right? So it's very important that you do not just decide, like we all did in single variable calculus, that every function is a graph and every graph is a function. We're just going to view these as the same thing. It just doesn't work. Okay, so instead, because we cannot make graphs work in so many cases, right, we're going to have to find other ways to represent functions with pictures. And those pictures will not be graphs. So, again, make sure you're very clear. Not all pictures are graphs. Not every picture you see can you treat as being a graph. You might have to interpret it in some other appropriate sense. Okay, so here's the next example. I think this is a underappreciated type of picture, at least in settings like this. This is what I like to call the literal picture. And the big idea is that if you have a function, keeping in mind what functions do, they take points in the domain and they do stuff to them to result in output values in the target. And we can just straight up literally draw that. Right? So for example, as in this case, my domain was R3. Okay, there's R3. That's my attempt to just very literally draw R3. And let's see, the target is R1. Okay, there you go. There's a picture after a fashion of R1. And I just kind of literally going to try to represent that what my function does is it takes points like that and it sends them to points like that. So it's pretty literal. Like that's what functions do. They take points out of a domain and they put images in to a target. Okay, now let's judge this picture. What do we think about this picture? Do we like this picture? And my first thought on this is I don't like it. I think there's something dramatically missing in this picture. Where's the rest of the function? I can only see what's happening at the one point. Shouldn't there be like a surface or a curve or something, right? Certainly, if you go back and look at the graph picture that we're all accustomed to, there's this curve here. And that curve, the geometry of this curve is extremely useful. The shape of this curve, by virtue of its slope or its concavity, tells me really important information, algebraic information about the function, namely how the derivatives behave. Right? So this curve isn't just a sort of a security blanket. There is information, valuable information encoded into the geometry of this shape. That's awesome. Where is the shape here? Right? So okay, that's my gripe about this picture. And now let me put that into perspective. Though. Oh yeah, question.
What happens if it's R4 though?
Oh yeah, then this crashes and burns too. Yeah, then I'm really out of luck. Yeah, and that does happen sometimes, that you have functions where you've just got so many variables and you just really can't draw pictures. And I've sadly been in that situation a few times, and you just got to limp along the best you can and accept that it's going to be hard. Yeah, right. Okay, so I'm going to now come to the defense of this picture and say it was a completely unfair comparison to compare this picture with this picture, because look at this. This was R1 to R1, right? And that's a much easier scenario. Here, R3 to R1 is a much harder scenario. So if we're going to have an apples to apples fair comparison, right, between these two different kinds of pictures, let's look back. What did the graph construction give me when I was trying to look at functions from R3 to R1? And it gave me crash and burn. Right? So the fair comparison here, before you judge, right, before you get, before that nose goes up in the air and you decide you don't like this picture, yeah, as opposed to what? What's your alternative? Right? This picture stinks. This picture doesn't exist. Stinks is a win. Right? In this scenario, it's way, way better than nothing. And in fact, not only is this better than nothing, this is actually pretty good in certain contexts. Let me show you a specific question that we're going to be entertaining in this class very soon, later this week, if I remember correctly. And that is, let's suppose I have one of these kinds of functions. And let's suppose that I know that there is a certain input point representing maybe where I am or the current state of a system or whatever. There's a point representing, in some sense, now. And I can look at its image. So under certain current parameters, here's the value of the function, whatever that means. And now here's a reasonable question. Perfectly natural and reasonable question to ask, and that is, suppose these parameters were to start changing, and how would I represent when these numbers x, y, z, when this point starts changing? Well, if it were changing, it would move with some velocity, and as that point moves with some velocity, then the image is going to start moving with some velocity. And given an input velocity, reasonable question to ask, what is the corresponding output velocity? And now, how do we answer that question? Yeah, we'll talk about that later. That's not the point here, right? The point is, we have a natural picture of the question on this literal sort of context. A point changing, an input point moving, results in an image moving, and we want to relate the input velocity to the output velocity. There is a picture here of the question, and something to get our hands on as we try to solve that. We'll solve the details of the problem later. Everybody buy it? Okay. All right. So next thing, let's talk about level sets. It's another kind of picture that we draw. Level sets are pre-images. Remember we talked about pre-images previously. Given an output, what's the corresponding input? Or quite possibly, looking back to here, given an output, there might be possibly several inputs. And remember, it's a little unfortunate, but the term pre-image can refer to a single point whose output is the given output value. But the word pre-image can also refer to the set of all such points that give that same output value. So the word pre-image can refer to the set, and then it can also refer to points in the set at pre-image. Okay, yeah.
So is it the points in the set, and that should be the input variable?
Points in the set what?
So the points in the set are the input variables that give off the output or the image? Or?
So the word pre-images refers to either a point like this, or possibly several points, or possibly the entire collection of points that when you put into the function give you the given output.
Yes, so they are input variables, right?
So what?
They are input variables.
Well, yeah. I mean, so a point has several different variable coordinates, but don't think about variables are very often a distraction, right? It's better to think of what goes in as being a point instead of as a bunch of coordinates, because it's just, I mean, it's really more natural to think of it as a point. Does that make sense?
It's the point that is put into the function.
Yes.
And then the is equal to.
That's right.
Okay.
That's right. Yeah. Okay. So let's see here. Where are we? Yeah. Okay. So again, a bunch of symbols describing what we mean by a level set. I think it's easiest to go through this by example. So let's look at, if I can get this to cooperate. There we go. Let's look at this specific example down here. And I'm going to pick a certain output value, 1. Right? 1 is an output value. This is the value that we're going to call B here. And given that output value B, the preimage for that output value, the level set then for that output value, is the collection of all of the input points for which the value of the function gives the prescribed output point. Right? That's just a straight up what a preimage is. So now writing this down, looking at this output value, z equals 1. Right? That output value, we're going to take the value of the function, right? The formula for the value of the function. We're going to ask what are the inputs that make the value of the function equal to b. So I want to know what are the x's and y's where x squared plus y squared is equal to 1. And those x's and y's, not hard to persuade yourself, are going to make a unit circle. And why? Well, because we happen to have studied this equation before. X squared plus y squared equals 1. Right? It's our old friend. That's a unit circle. Okay, so that is our first example of a level set. Now, a level set by itself usually doesn't show you a whole heck of a lot. It's usually nice to have several level sets to look at. So we're going to play the same game here now with different output values. Let's look at 2. Right? That's an output value. I can ask for that output value, what are the corresponding input values? And again, that make the value of the function equal to my color choices, to that output value 2. And those output values, those input values, the x's and y's, the set of solutions to this equation is a slightly larger circle. And again, we just happen to remember, right? X squared plus y squared equals 2. It's a circle of radius square root of 2. Yeah.
How would you go about finding a level set for a more complicated function?
Oh yeah, the algebra can get real weird. Yeah, totally. Yeah. So yeah, I'm not saying that these methods are all going to be easy to use, right? But what we're going to focus on right now isn't so much the actual mechanics of creating these level sets in this case, but what does it mean? Like, what is the process in general, right? What does it even mean to talk about level sets? Yeah, right. Okay. Yeah.
So are there technically an infinite number of level sets
Yes.
for any given function?
Well, that's right, because there's an infinite number of different output values that you could pick, and then correspondingly different level sets that you would get as a result. Absolutely. So in fact, and you'll notice the more output values you pick, the more curves you get, and the more, in some sense, complete picture you have of what's going on with the function in some sense. And so here's a nice example. And by the way, this is my favorite sort of personal kind of metaphor. Right? When you're thinking about level sets, in some sense, I'm always visualizing level sets as being kind of like this. And let's think of specifically the altitude function. By altitude function, what I mean is you give me a point on the map, longitude and latitude. You can go to that point on the globe and have your altimeter and measure what is the altitude of the ground at that point on the map. Right? So that's what I mean by the altitude function. So if y'all have ever gone hiking or contemplated going hiking, or if you've ever zoomed in just exactly right on Google Maps or whatever, then you may have seen these things called contour lines. Contour lines are level sets. So for example, let's set a particular altitude, maybe 300 feet, not that it matters, whatever. I can ask, okay, what points on this map have an altitude of 300 feet? And you're going to get a bunch of points, typically in a curve, something like that. And those are the points where the altitude is 300 feet. And then you can go on from there and say, okay, all right, well, fine, but how about 400 feet? And maybe this is 400 feet. And then et cetera, et cetera. So what about 500 feet? Okay, maybe something like that for 500 feet. And then off you go. I mean, keep going. 600, 700, 800, right? And you get these various different curves like that. And keeping in mind that as you go to the right in altitude, right, the corresponding colors here represent higher altitudes on this map. And you can kind of probably visualize in some sense, given the way I've done the color coding here, what we have here is kind of sort of a mountain. And that's the mountaintop, about right there. Right? And you can almost kind of, in some sense, get an visual idea of the shape of the mountain, maybe even a little bit. Right? Now, is it as good as a graph? No. I mean, pros and cons, I guess. But this is not the same as actually looking at the mountain. And there's gaps. Like, I don't have any information about what's going on in here. I didn't draw those level sets in here, right? But it's better than nothing. And it has its merits. So here, by the way, is a real contour map. Let's see here. Let me switch to here. Here we go. This is an actual. I think this is from the USGS. So this is the government puts out maps of mountainous areas. This is called a topographical map, and these curves like that are called contour lines, but they're level sets of the altitude function. This is a picture of a bunch of level sets, right? And now that's a lot of curves, and it makes for a complicated picture, but there's a lot of really valuable information that you can see on these maps. And I'm going to just kind of talk through some examples of this. And by the way, this is a mountain that I climbed when I was about y'all's age. And so I can comment, for example, as you're hiking along in here, as you're following this path right here, it's uphill, but it's not so bad. Not that bad. By the way, for whatever it's worth, I don't know why they chose this, but every pair of contiguous lines are 40 feet altitude different. I don't know why 40, but that's just what they decided. So anyway, 40 feet. And notice, as you're hiking along this path right here, look at all this distance. You get to cover a substantial, that's a few hundred feet, several hundred feet that you get to walk before gaining 40 feet of altitude. So not so steep. Okay. Whereas on the other hand, if you were to go that way, oh my God, right, way steeper. That's brutal. Let's see if I can zoom in here. I am out of that business. When I was young, maybe, right? But instead of having that much distance over which to gain 40 feet of altitude, now you've got that much distance over which to gain 40 feet of altitude. That's quite steep. That'd be like 45 degrees or something like that. That's no fun. Not for me. Okay, so now while we're here, here's a an idea that we can make some sense out of. So notice that the trail here doesn't just go basically straight up the mountain. Notice they do this zigzaggy thing, right? So why are they doing all that zigzag? Well, they're doing that zigzag because if you look at, let's say, for example, from here to there, well, we're gaining, what's that now? 1, 2, 3, 4, 5, 6, 7, 4. That's nearly 300 feet of elevation gain, right, over not very much distance. That's a really steep climb. But because they did this zigzag thing, right, when you actually follow the trail, you get to spread out that 300 feet of elevation gain. It's the same 300 feet of elevation gain, but you get to spread it out over a greater horizontal distance, and so it's not as steep. And so it's more palatable, for old guys like myself to be able to realistically have a chance of being able to do. Okay. All right. And then one last thing I'm going to point out while we're here. So, again, quite steep. Look how close together these lines are. Keep in mind, the closer together the lines, the more steep it is. Look at this right here. They're so close together. This is so steep, it looks vertical. And when you're standing right there, as I did, right, and you're looking that way, it feels like it's straight down. And now you can tell it's not, right? I mean, you can tell those lines are not right on top of each other. There is some separation, but it's like about, I'm going to say it's about like that. It's about that steep. It's bonkers steep. It's not the kind of thing that what I would consider to be sane people would. I would never climb that myself. That crazy people will, but yes.
What if there's like an overlook, like a cliff?
Oh, like
How would that?
And if it like hangs over, then it's not then there's a problem, right? It'd be a hard thing to represent. This is made for the idea that we're looking at that for every map coordinate, longitude and latitude, that there is a single well-defined altitude. And as you describe, if the land kind of like does like that, then for any given map, for this map coordinate, there's sort of several different, the surface of the Earth has several different altitudes. And so this kind of a picture just doesn't really make sense. Yeah, so thankfully that doesn't happen super often. Yeah, yes?
Is there a way to indicate if it's steep going down rather than steep going up?
Well, it's really the same steepness though,
But from like, I don't know.
But okay, all right. It sounds like you had a question that maybe you didn't phrase quite the way you wanted. Feel free to think about it, and if you want to talk to me after class, totally fine. Yeah, right. Okay, so useful information that you can see on the basis of these kinds of pictures. And again, this is notice a two-dimensional picture, and you can take this picture, you can print it out and fold it up on a piece of paper, fold it up, put it in your pocket, no problem. Off you hike, right? And you've got a clear picture of what's where and how steep it is on a piece of paper. Whereas, if you were to try to make a graph of the altitude function, the mountain is the graph, right? And I guess you could make a little miniature model of the mountain, and you could have this little miniature paper mache little shaped thing, but now you're going to be carrying around this big thing while you're hiking. It just doesn't make any sense. So practically speaking, in a situation like this, level sets are way more convenient to work with than graphs. Okay. All right, let's see here. And I have 30 seconds. All right, we're just going to have to draw the line right here. Okay, so picking up here on Wednesday. See y'all later. Have a good one. Just 1 second here.